All right, hi everyone, and welcome back. My name is Ava, and before we dive into Lecture 2 of 6S191, which is going to be on deep sequence modeling, I'll just note that, as you probably noticed, we're running a little bit late. So we're going to proceed with the lecture in full and in completion, and at the time it ends, then we'll transition to the software lab portion of the course just immediately after, at the time that this lecture ends. And I'll make a note about the structure and how we're going to run the software labs at the end of my lecture. OK, so in Alexander's first lecture, we learned about really the essentials of neural networks and feed-forward models and how to construct them. And so now we're going to turn our attention to applying neural networks to tasks that involve modeling sequences of data. And we'll see why these sorts of tasks require a fundamentally different type of network architecture from what we've seen so far. And to build up to that point, we're going to walk through step by step, building up intuition about why modeling sequences is different and important, and start back with our fundamentals of feed-forward networks to build up to the models we'll introduce in this lecture. All right, so let's dive into it. Let's first motivate the need for sequence modeling and what we mean in terms of sequential data with a super intuitive and simple example. So suppose we have this picture of a ball, and our task is to predict where this ball is going to travel to next. Now, if I don't give you any prior information on the ball's history, any guess on its next position is just going to be that, a random guess. But now instead, if in addition to the current location of the ball, I also gave you some information about its previous locations, now our problem becomes much easier, and I think we can all agree that we have a sense of where this ball is going to next. And beyond this simple example, the fact of the matter is that sequential data is all around us. For example, audio, like the waveform of my voice speaking to you, can be split up into a sequence of sound waves, while text can be split up into a sequence of characters or a sequence of words. And beyond these two examples, there are many, many more cases in which sequential processing may be useful, from medical signals like EKGs, to stock prices, to DNA sequences, and beyond. So now that we've gotten a sense of what sequential data looks like, let's consider applications of sequential modeling in the real world. In Alexander's first lecture, we learned about this notion of feed-forward models that operate sort of on this one-to-one fixed setting, right? A single input to a single output. And he gave the very simple example of a binary classification task predicting whether you, as a student, will pass or fail this class. Of course, we all hope you will pass. But in this example, there's no real component of time or sequence, right? In contrast with sequence modeling, we can now handle a vast variety of different types of problems where, for example, we have a sequence of temporal inputs and potentially a sequential output. So let's consider one example, right, where we have a natural language processing task, where we have a tweet, and we want to classify the emotion or the sentiment associated with that tweet, mapping a sequence of words to a positive or negative label. We can also have a case where our input initially may not have a time dimension. So for example, we have this image of a baseball player throwing a ball. But instead, the output that we want to generate has a temporal or sequential component, where we now want to caption that image with some associated text. And finally, we can have a final case where we have a sequential input and we want to map it to a sequential output. For example, in the case of translating text from one language to another. And so sometimes it can be really challenging to kind of wrap your head around and get the idea about how we can add a new temporal dimension to our models. And so to achieve this understanding, what I want to do is really start from the fundamentals and revisit the concept of the perceptron that Alexander introduced and go step by step from that foundation to develop an understanding of what changes we need to make to be able to handle sequential data. So let's recall the architecture and the diagram of the perceptron, which we studied in the first lecture. We define a set of inputs, and we have these weights that are associated with connecting those inputs to an internal node, and we can apply those weights, apply a nonlinearity, and get this output. And we can extend this now to a layer of individual neurons, a layer of perceptrons, to yield a multidimensional output. And in this example, we have a single layer of perceptrons, shown in green, taking 3 inputs, shown in blue, predicting 4 outputs in purple. But does this have a notion of time or of sequence? Not yet. Let's simplify that diagram, right? What I've done here is I've collapsed that layer of those 4 perceptrons into this single green box. And I've collapsed those nodes of the input and the output into these single circles that are represented as vectors. So our inputs, x, are some vectors of a length m, and our outputs are vectors of another length, n. Still here, what we're considering is an input at a specific time denoted by t, nothing different from what we saw in the first lecture, and we're passing it through a feed-forward model to get some output. What we could do is we could have fed in a sequence to this model by simply applying the same model, that same series of operations, over and over again, once for each time step in our sequence. And this is how we can handle these individual inputs, which occur at individual time steps. So first, let's just rotate this same diagram. I've taken it from a horizontal view to a vertical view. We have this input vector at some time step t. We feed it into our network, get our output. And since we're interested in sequential data, let's assume we don't just have a single time step. We now have multiple individual time steps, starting from t equals 0, our first time step in our sequence, and extending forward, right? Again, now we're treating the individual time steps as isolated time steps, right? We don't yet have a notion of the relationship between time step 0 and time step 1, time step 2, and so on and so forth. And what we know from the first lecture is that our output vector at a particular time step is just going to be a function of the input at that time step. What could be the issue here, right? Well, we have this transformation, yeah, but this is inherently sequential data, and it's probably in a sequence for some important reason, and we don't yet have any sort of interdependence or notion of interconnectedness across time steps here. And so if we consider the output at our last time step, right, the fundamental point is that that output is related to the inputs at the previous time steps. How can we capture this interdependence? What we need is a way to relate the network's computations at a particular time step to its prior history and its memory of the computations from those prior time steps, passing information forward, propagating it through time. And what we consider doing is actually linking the information and the computation of the network at different time steps to each other via what we call a recurrence relation. And specifically, the way we do this in recurrent models is by having what we call an internal memory or a state, which we're going to denote as h of t. And this value, h of t, is maintained time step to time step, and it can be passed forward across time. And the idea and the intuition here is we want this state to try to capture some notion of memory. And what this means for the network's computation, its output, is that now our output is dependent not only on the input at a particular time step, but also this notion of the state, of the memory that's going to be passed forward from the prior time step. Right? And so this output, just to make this very explicit, this output at a particular time step t depends both on the input as well as the past memory. And that past memory is going to capture the prior history of what has occurred previously in the sequence. And because this output, y of t, is a function of both current input, past memory, what this means is we can define and describe these types of neurons in terms of a recurrence relation. And so on the right, you can see how we visualize these individual time steps as sort of being unrolled, extended across time. But we could also depict this same relationship via a cycle, which I've shown on the left, which shows and highlights this concept of a recurrence relation. All right, so hopefully this builds up some intuition about this notion of recurrence and why it can help us in sequential modeling tasks. And this intuition that we've built up from starting with the feed-forward model is really the key to the recurrent neural network, or RNNs. And we're going to continue to build up from this foundation and build up our understanding of how this recurrence relation defines the behavior of an RNN. So let's formalize this just a bit more, right? The key idea that I mentioned, and I'm going to keep driving home, is that the RNN maintains this internal state, h of t, which is going to be updated at each time step as the sequence is processed. And we do this by applying this recurrence relation at every time step, where our cell state is now a function, our cell state h of t is now a function of the current input, x of t, as well as the prior state, h of t minus 1. And importantly, this function is parameterized by a set of weights w, and this set of weights is what we're actually going to be learning through our network over the course of training as the model is being learned and as these weights are being updated, right? And the key point here is that this set of weights, w, is the same across all time steps that are being considered in the sequence. And this function that computes this hidden state is also the same. We can also step through this intuition behind the RNN algorithm in sort of pseudocode to get a better sense of how these networks work. So we can begin by initializing our RNN, right? What does it take to initialize it? Well, first we have to initialize some first hidden state, which we're going to do with a vector of zeros. And we're going to consider a sentence that's going to serve as our input sequence to the model. And our task here is to try to predict the next word that's going to come at the end of this sentence. And our recurrence relation is captured by this loop, where we're going to iterate through the words in the sentence. And at each step, we're going to feed both the current word being considered as well as the previous hidden state into our RNN model. And that's going to output a prediction for what the likely next word is, and also update its internal computation of the hidden state. And finally, our token prediction that we're interested in at the end is the RNN's output after all the words, all the time points in the sequence have been considered. And that generates our prediction for the likely next word. And so that hopefully provides more intuition about how this RNN algorithm is working. And if you notice, the internal computation of the RNN includes both this internal state output, as well as ultimately trying to output the prediction that we're interested in, our output vector y of t. So to walk through how we actually derive this output vector, let's step through this. What we do is, given our input vector, we pass that in to compute the RNN's internal state computation. And breaking this function down, what it's doing is just a standard neural net operation, just like we saw in the first lecture, right? It consists of multiplication by weight matrices, right, donated as W. And in this case, we're going to multiply both the past hidden state by a weight matrix W, as well as the current input x of t by another weight matrix. And then we're going to add them together and apply a nonlinearity. And you'll notice, as I just mentioned, right, because we have these two inputs to the state update equation, we have these two independent weight matrices. And the final step is to actually generate the output for a given time step, which we do by taking that internal state and simply modifying it, following a multiplication by another weight matrix, and then using this as our generated output. And that's it. That's how the RNN updates its hidden state and also produces an output at a given time step. So far, right, we've seen the RNNs depicted largely as having these loops that feed back in on themselves. And as we built up from, we can also represent this loop as being unrolled across time, where effectively, starting from the first time step, we have this unrolled network that we can continue to unroll across time from time step 0 to our end time step t. And in this diagram, let's now formalize things a little bit more. We can also make the weight matrices that compute, that are applied to the input very explicit. And we can also annotate our diagram with the weight matrices that relate the prior hidden state to the current hidden state. And finally, our predictions at individual time steps are generated by a separate weight matrices. Okay, so as I mentioned, right, the key point is that these weight matrices are reused across all of the individual time steps. Now, our next step that you may be thinking of is, okay, this is all great. We figured out how to update the hidden state. We figured out how to generate the output. How do we actually train this thing, right? Well, we'll need a loss, because as Alexander mentioned, the way we train neural networks is through this optimization, this iterative optimization of a loss function or an objective function. And as you may predict, right, we can generate an individual loss for each of these individual time steps according to what the output at that time step is. And we can generate a total sum loss by taking these time steps and summing them all together. And when we make a forward pass through our network, this is exactly what we do, right? We generate our output predictions, and we sum the loss functions across individual time steps to get the total loss. Now, let's next walk through an example of how we can implement an RNN from scratch. The previous code block that I showed you was kind of an intuitive pseudocode example. And here now we're going to get into things in a little bit more detail and build up the RNN from scratch. Our RNN is going to be defined as a neural network layer, and we can build it up by inheriting from the neural network layer class that Alexander introduced in the first lecture. And as before, we're going to start by initializing our weight matrices and also initializing the hidden state to 0. Our next step, which is really the important step, is defining the call function, which is what actually defines the forward pass through our RNN model. And within this call function, the key operations are as follows. We first have an update of the hidden state, right, according to that same equation we saw earlier, incorporating the previous hidden state, incorporating the input, summing them, passing them through a nonlinearity. We can then compute the output, transforming the hidden state. And finally, at each time step, we return both the current output and our hidden state. That's it. That's how you can code up an RNN line by line and define the forward pass. But thankfully, TensorFlow has very, very conveniently summarized this already and implemented these types of RNN cells for us in what they wrap into the simple RNN layer. And you're going to get some practice using this, this class of neural network layer in today's software lab. All right, so to recap, right, we've seen how the function and the computation of RNNs by first moving from the one-to-one computation of a traditional feed-forward vanilla neural network, and seeing how that breaks down when considering sequence modeling problems. And as I mentioned, right, we can apply this idea of sequence modeling and of RNNs to many different types of tasks. For example, taking a sequential input and mapping it to one output. Taking a static input that's not resolved over time and generating a sequence of outputs, for example, a text associated with an image. Or translating a sequence of inputs to a sequence of outputs, which can be done in machine translation, natural language processing, and also in generation. So for example, in composing new musical scores entirely using recurrent neural network models. And this is what you're going to get your hands-on experience with in today's software lab. And beyond this, right, you all come from a variety of different backgrounds and interests and disciplinary domains. So I'm sure you can think of a variety of other applications where this type of architecture may be very useful. Okay, so to wrap up this section, right, this simple example of RNNs kind of motivates a set of concrete design criteria that I would like you to keep in mind when thinking about sequence modeling problems. Specifically, whatever model we design needs to be able to handle sequences of variable length, to track long-term dependencies in the data, to be able to map something that appears very early on in the sequence to something related later on in the sequence, to be able to preserve and reason and maintain information about order, and finally to share parameters across the sequence to be able to keep track of these dependencies. And so most of today's lecture is going to focus on recurrent neural networks as a workhorse neural network architecture for sequence modeling criteria, design problems. But we'll also get into a new and emerging type of architecture called transformers later on in the lecture, which I think you'll find really exciting and really interesting as well. Before we get into that, I'd like to spend a bit of time thinking about these design criteria that I enumerated and why they're so important in the context of sequence modeling, and use that to move forward into some concrete applications of RNNs and sequence models in general. So let's consider a very simple sequence modeling problem. Suppose we have this sentence, right? This morning I took my cat for a walk. And our task here is to use some prior information in the sentence to predict the next word in the sequence, right? This morning I took my cat for a, predict the next word, walk. How can we actually go about doing this, right? I've introduced the intuition and the diagrams and everything about the recurrent neural network models, but we really haven't started to think about, okay, how can we even represent language to a neural network? How can we encode that information so that it can actually be passed in and operated on mathematically? So that's our first consideration, right? Let's suppose we have a model. We're inputting a word, and we want to use our neural network to predict the next word. What are considerations here, right? Remember, the neural network, all it is it's just a functional operator. They execute some functional mathematical operation on an input. They can't just take a word as a string or as a language, as a sequence of language characters, passed in as is. That's simply not going to work, right? Instead, we need a way to represent these elements, these words, numerically, to be fed in to our neural network as a vector or a matrix or an array of numbers, such that we can operate on it mathematically and get a vector or array of numbers out. This is going to work for us. So how can we actually encode language, transform it into this vector representation? The solution is this concept of what we call an embedding. And the idea is that we're going to transform a set of indices, which effectively are just identifiers for objects, into some vector of fixed size. So let's think through how this embedding operation could work for language data. For example, for this sequence that we've been considering, right? We want to be able to map any word that could appear in our body of language, our corpus, into a fixed-sized vector. And so the first step to doing this is to think about the vocabulary, right? What's the overall space of unique words in your corpus, in your language? From this vocabulary, we can then index by mapping individual words to numerical unique indices. And then these indices can then be mapped to an embedding, which is just a fixed length vector. One way to do this is by taking a vector, right, that's length is just going to equal the total number of unique words in our vocabulary. And then we can indicate what word that vector corresponds to by making this a sparse vector that's just binary. So it's just zeros and ones, and at the index that corresponds to that word, we're going to indicate the identity of that word with a 1, right? And so in this example, our word is cat, and we're going to index it at the second index. And what this is referred to is a one-hot embedding. It's a very, very popular choice of embedding, which you will encounter across many, many different domains. Another option to generating an embedding is to actually use some sort of machine learning model, it can be a neural network, to learn an embedding. And so the idea here is from taking an input of words that are going to be indexed numerically, we can learn an embedding of those words in some lower dimensional space. And the motivation here is that by introducing some sort of machine learning operation, we can map the meaning of the words to an encoding that is more informative, more representative, such that similar words that are semantically similar in meaning will have similar embeddings. And this will also get us our fixed length encoding vector. And this idea of a learned embedding is a super, super powerful concept that is very pervasive in modern deep learning today. And it also motivates a whole nother class of problems called representation learning, which is focused on how we can take some input and use neural networks to learn a meaningful encoding of that input for our problem of choice. Okay, so going back to our design criteria, right, we're first going to be able to try to handle variable sequence lengths. We can consider, again, this problem of trying to predict the next word. We can have a short sequence, we can have a longer sequence, or an even longer sequence, right? But the whole point is that we need to be able to handle these variable length inputs, and feed-forward networks are simply not able to do this because they have inputs of fixed dimensionality. But because with RNNs, we're unrolling across time, we're able to handle these variable sequence lengths. Our next criteria is that we need to be able to capture and model long-term dependencies in the data. And so you can imagine an example like this, where information from early on in the sentence is needed to accurately make a prediction later on in the sentence. And so we need to be able to capture this longer-term information in our model. And finally, we need to be able to retain some sense of order, right, that could result in differences in the overall context or meaning of a sentence. So in this example, these two sentences have the exact same words, repeated the exact same number of times, but the semantic meaning is completely different because the words are in different orders. And so hopefully this example shows a very concrete and common example of sequential data, right, language, and motivates how these different design considerations play into this general problem of sequence modeling. And so these points are something that I'd really like for you to take away from this class and keep in mind as you go forward implementing these types of models in practice. Our next step, as we walk through this lecture on sequence modeling, is to actually go through very briefly on the algorithm that's used to actually train recurrent neural network models. And that algorithm is called backpropagation through time. And it's very, very related to the backpropagation algorithm that Alexander introduced in the first lecture. So if you recall, the way we train feed-forward models is go from input and make a forward pass through the network, going from input to output. And then backpropagate our gradients back downwards through the network, taking the derivative of the loss with respect to the weights learned by our model, and then shifting and adjusting the parameters of these weights in order to try to minimize the loss over the course of training. And as we saw earlier for RNNs, they have a little bit of a different scenario here because our forward pass through the network consists of going forward across time, computing these individual loss values at the individual time steps, and then summing them together. To backpropagate, instead of backpropagating errors through a single feed-forward network, now what we have to do is backpropagate error individually across each time step and then across all the time steps, all the way from where we currently are in this sequence to the beginning of the sequence. And this is the reason why this algorithm is called backpropagation through time, because as you can see, errors flow backwards in time to the beginning of our data sequence. And so taking a closer look at how these gradients flow across this RNN chain, what you can see is that between each time step, we need to perform these individual matrix multiplications, right? Which means that computing the gradient, that is, taking the loss with respect to an internal state and the weights of that internal state, requires many, many matrix multiplications involving this weight matrix, as well as repeated gradient computation. So why might this be problematic? Well, If we have many of these weight values or gradient values that are much, much, much larger than 1, we could have a problem where during training our gradients effectively explode. And the idea behind this is the gradients are becoming extremely large due to this repeated multiplication operation, and we can't really do optimization. And so a simple solution to this is called gradient clipping, just trimming the gradient values to scale back bigger gradients into a smaller value. We can also have the opposite problem, where now our weight values are very, very small. And this leads to what is called the vanishing gradient problem, and is also very problematic for training recurrent neural models. And we're going to touch briefly on 3 ways that we can mitigate this vanishing gradient problem in recurrent models. First, choosing our choice of activation function, initializing the weights in our model intelligently, and also designing our architecture of our network to try to mitigate this issue altogether. The reason why, before we do that, to take a step back, right, the reason why vanishing gradients can be so problematic is that they can completely sabotage this goal we have of trying to model long-term dependencies. Because we are multiplying many, many small numbers together, what this effectively biases the model to do is to try to preferentially focus on short-term dependencies and ignore the long-term dependencies that may exist. And while this may be okay for simple sentences like the clouds are in the blank, it really breaks down in longer sentences or longer sequences where information from earlier on in the sequence is very important for making a prediction later on, in the case of this example here. So how can we alleviate this? Our first strategy is a very simple trick that we can employ when designing our networks. We can choose our activation function to prevent the gradient from shrinking too dramatically. And the ReLU activation function is a good choice for doing this because in instances where our input x is greater than 0, it automatically boosts the value of the activation function to 1, whereas other activation functions don't do that. Right. Another trick is to be smart in how we actually initialize the parameters in our model. What we can do is initialize the weights that we set to the identity matrix, which prevents them from shrinking to 0 too rapidly during backpropagation. And the final and most robust solution is to use a more complex recurrent unit that can effectively track long-term dependencies in the data. And the idea here is that we're going to introduce this computational infrastructure called the gate, which functions to selectively add or remove information to the state of the RNN. And this is done by standard operations that we see in neural networks. For example, sigmoid activation functions, pointwise matrix multiplications. And the idea behind these gates is that they can effectively control what information passes through the recurrent cell. And today we're going to touch very briefly on one type of gated cell called a LSTM, a long short-term memory network. And they're fairly good at using this gating mechanism to selectively control information over many time steps. And so I'm not going to get into the details, right, because we have more interesting things to touch on in our limited time. But the key idea behind LSTMs is they have that same chain-like structure as a standard RNN, but now the internal computation is a little bit more complex, right? We have these different gates that are effectively interacting with each other to try to control information flow. And you would implement the LSTM in TensorFlow just as you would a standard RNN. And while that diagram, I just blew past that, right? The gated structure, we could spend some time talking about the mathematics of that, but really what I want you to take away from this lecture is the key concepts behind what the LSTM is doing internally. So to break that down, the LSTM, like a standard RNN, is just maintaining this notion of cell state, but it has these additional gates which control the flow of information, functioning to effectively eliminate irrelevant information from the past, keeping what's relevant, keeping what's important from the current input, using that important information to update the internal cell state, and then outputting a filtered version of that cell state as the predictive output. And what's key is that because we incorporate this gated structure, in practice, our backpropagation through time algorithm actually becomes much more stable, and we can mitigate against the vanishing gradient problem by having fewer repeated matrix multiplications that allow for a smooth flow of gradients across our model. Okay, so now we've gone through the fundamentals of RNNs in terms of their architecture and training, and I'd next like to consider a couple of concrete examples of how we can use recurrent neural models. The first is, let's imagine we're trying to use a recurrent model to predict the next musical note in a sequence and use this to generate brand new musical sequences. What we can do is we can treat this as a next time step prediction problem, where you input a sequence of notes and the output at each time step is the most likely next note in the sequence. And so, for example, it turns out that this very famous classical composer named Franz Schubert had what he called a very famous unfinished symphony, and that was left, as the name suggests, partially undone, and he did not get a chance to actually finish composing the symphony before he died. And a few years ago, some researchers trained a neural network model on this on the prior movements of that symphony to try to actually generate new music that would be similar to Schubert's music to effectively finish the symphony and compose 2 new movements. So we can actually take a listen to what that result turned out like. So hopefully you were able to hear that and appreciate the point that maybe there are some classical music aficionados out there who can recognize it as being stylistically similar, hopefully, to Schubert's music. And you'll get practice with this exact same task in today's lab, where you'll be training a recurrent model to generate brand new Irish folk songs that have never been heard before. As another cool example, which I kind of motivated at the beginning of the lecture, we can also do a classification task where we take an input sequence and try to predict a single output associated with that sequence. For example, taking a sequence of words and assigning an emotion or a sentiment associated with that sequence. And one use case for this type of task is in tweet sentiment classification. So training a model on a bunch of tweets from Twitter and using it to predict a sentiment associated with given tweets. So, for example, we can train a model like this with a bunch of tweets. Hopefully, we can train an RNN to predict that this first tweet about our course has a positive sentiment, but that this other tweet about winter weather is actually just having a negative sentiment. Okay, so at this point, we focus exclusively on recurrent models. And it's actually fairly remarkable that with this type of architecture, we can do things that seem so complex as generating brand new classical music. But let's take a step back, right? With any technology, there are going to be strengths and there are going to be limitations. What could be potential issues of using recurrent models to perform sequence modeling problems? The first key limitation is that these network architectures fundamentally have what we like to think of as an encoding bottleneck. We need to take a lot of content, which may be a very long body of text, many different words, and condense it into a representation that can be predicted on. And information can be lost in this actual encoding operation. Another big limitation is that recurrent neurons and recurrent models are not efficient at all. Right? They require sequentially processing information, taking time steps individually. And this sequential nature makes them very, very inefficient on the modern GPU hardware that we use to train these types of models. And finally, and perhaps most importantly, while we've been emphasizing this point about long-term memory, the fact is that recurrent models don't really have that high of memory capacity to begin with. While they can handle sequences of length on the order of tens or even hundreds with LSTMs, they don't really scale well to sequences that are of length of thousands or 10,000s of time steps. How can we do better, and how can we overcome this? So to understand how to do this, right, let's go back to what our general task is with sequence modeling. We're given some sequence of inputs. We're trying to compute some sort of features associated with those inputs and use that to generate some output prediction. And with RNNs, as we saw, we're using this recurrence relation to try to model sequence dependencies. But as I mentioned, these RNNs have these three key bottlenecks. What is the opposite of these three limitations? If we had any capability that we desired, what could we imagine? The capabilities that we'd really like to achieve with sequential models is to have a continuous stream of information that overcomes the encoding bottleneck. We'd like our model to be really fast, to be parallelizable rather than being slow and dependent on each of the individual time steps. And finally, we want it to be able to have long memory. And the main limitation of RNNs when it comes to these capabilities is that they process these individual time steps individually due to the recurrence relation. So what if we could eliminate the recurrence relation entirely, do away with it completely? One way we could do this is by simply taking our sequence and squashing everything together, concatenating those individual time steps such that we have one vector of input with data from all time points. We can feed it into a model, calculate some feature vector, and then generate an output, which maybe we hope makes sense, right? Naively, a first approach to do this may be to take that squashed, concatenated input, pass it into a fully connected network. And yay, congrats, we've eliminated the need for recurrence. But what are our issues here, right? This is totally not scalable, right? Our dense network is very, very densely connected, right? It has a lot of connections, and our whole point of doing this was to try to scale to very long sequences. Furthermore, we've completely eliminated any notion of order, any notion of sequence. And because of these two issues, our long memory that we want all along is also made impossible. And so this approach is definitely not going to work. We don't have a notion of what points in our sequence is important. Can we be more intelligent about this? And this is really the key idea behind the next concept that I'm going to introduce in the remaining time. And that's this notion of attention, right? Which intuitively we're going to think about the ability to identify and attend to parts of an input that are going to be important. And this idea of attention is an extremely powerful and rapidly emerging mechanism for modern neural networks. And it's the core foundational mechanism for this very, very powerful architecture called transformers. You may have heard of transformers before in popular news, media, what have you. And the idea, when you maybe want to try to look at the math and the operation of transformers, can seem very daunting. It was definitely daunting for me, as it tends to be presented in a pretty complex and complicated way. But at its core, this attention mechanism, which is the really key insight into transformers, is actually a very elegant and intuitive idea. We're going to break it down step by step so you can see how it's computed and what makes it so powerful. To do that, we're specifically going to be talking about this idea of self-attention. And what that means is the ability to take an input and attend to the most important parts of that input. I think it's easiest to build up that intuition by considering an image. So let's look at this picture of our hero, Iron Man. How do we figure out what's important? A naive way could just be to scan across this image pixel by pixel. But as humans, we don't do this. Our brains are able to immediately pick up what is important in this image just by looking at it. That's Iron Man coming at us. And if you think about it, right, what this comes down to is the ability to identify the parts that are important to attend to and be able to extract features from those regions with high attention. And this first part of this problem is very, very similar conceptually to search. And to build up understanding of this attention mechanism, we're going to start there first, search. How does search work? So maybe sitting there listening to my lecture, you're thinking, wow, this is so exciting, but I want to learn even more about neural networks. How can I do this? One thing you could do is go to our friend the internet, do a search, and have all the videos on the internet accessible to you, and you want to find something that matches your desired goal. So let's consider YouTube, right? YouTube is a giant database of many, many, many videos. And across that database, they're ranging of different topics. How can we find and attend to a relevant video to what we're searching for, right? The first step you do is to input some query into the YouTube search bar. Your topic is deep learning. And what effectively can be done next is that for every video in this database, we're going to extract some key information, which we call the key. It's the title maybe associated with that video. And to do the search, what can occur is the overlaps between your query and the keys in that database are going to be computed. And as we do this, at each check we make, we'll ask, how similar is that key, the title of the video, to our query, deep learning? Our first example, right, this video of a turtle, is not that similar. Our second example, lecture from our course, is similar. And our third example, Kobe Bryant, is not similar. And so this is really this idea of computing what we'll come to see as an attention mask, measuring how similar each of these keys, these video titles, is to our query. Our next and final step is to actually extract the information that we care about based on this computation, the video itself. And we are going to call this the value. And because our search was implemented with a good notion of attention, gratefully we've identified the best deep learning course out there for you to watch. And I'm sure all of you sitting there can hopefully relate and agree with that assessment. Okay, so this concept of search is very, very related to how self-attention works in neural networks like transformers. So let's go back from our YouTube example to sequence modeling. For example, where we have now this sentence, he tossed the tennis ball to serve. And we're going to break down step by step how self-attention will work over this sequence. First, let's remember what we're trying to do. We're trying to identify and attend to the most important features in this input without any need for processing the information time step by time step. We're going to eliminate recurrence. And what that means is that we need a way to preserve order information without recurrence, without processing the words in the sentence individually. The way we do this is by using an embedding that is going to incorporate some notion of position. And I'm going to touch on this very, very briefly for the sake of time. But the key idea is that you compute a word embedding, you take some metric that captures position information within that sequence, you combine them together, and you get an embedding and an encoding that has this notion of position baked in. We can talk about the math of this further if you like, but this is the key intuition that I want you to come away with. Our next step, now that we have some notion of position from our input, is to actually figure out what in the input to attend to. And that relates back to our search operation that I motivated with the YouTube example. We're going to try to extract the query, the key, and the value features. And recall, we're trying to learn a mechanism for self-attention, which means that we're going to operate on the input itself and only on the input itself. What we're going to do is we're going to create 3 new and unique transformations of that embedding. And these are going to correspond to our query, our key, and our value. All we do is we take our positional embedding, we take a linear layer, and do a matrix multiplication. That generates one output, a query. Then we can make a copy of that same positional embedding. Now we can take a separate and independent, a different linear layer, do the matrix multiplication, and get another transformation of that output. That's our key. And similarly, do this also for the value. And so we have these 3 distinct transformations of that same positional embedding, our query, our key, and our value. Our next step, right, is to take these 3 features, right? And actually compute this attention weighting, figuring out how much attention to pay to and where. And this is effectively thought of as the attention weighting. And if you recall from our YouTube example, we focused on the similarity between our query and our key. And in neural networks, we're going to do exactly the same, right? So if you recall, these query and key features are just numeric matrices or vectors. How can we compute their similarity, their overlap? So let's suppose we have two vectors, q and k. And for vectors, as you may recall from linear algebra or calculus, we can compute the similarity between these vectors using a dot product and then scaling that dot product. And this is going to quantify our similarity between our query and our key vectors. This metric is also known as the cosine similarity, and we can apply the same exact operation to matrices, where now we have a similarity metric that captures the similarity between the query matrix and the key matrix. Okay, let's visualize what the result of this operation could actually look like and mean. Remember, we're trying to compute this self-attention. We compute this dot product of our query and our key matrices. We apply our scaling. And our last step is to apply a function called the softmax, which just squashes every value so that it falls between 0 and 1. And what this results in is a matrix where now the entries reflect the relationship between the components of our input to each other. And so in this sentence example, he tossed the tennis ball to serve. What you can see with this heat map visualization is that the words that are related to each other, tennis, serve, ball, tossed, have a higher weighting, a higher attention. And so this matrix is what we call the attention weighting. And it captures where in our input to actually self-attend to. Our final step is to use this weighting matrix to actually extract features with high attention. And we simply do this, it's super elegant, by taking that attention weighting, multiplying it by our value matrix, and then getting a transformed version of what was our value matrix. And this is our final output. This reflects the features that correspond to high attention. Okay, that's it, right? I know that could be fast, so let's recap it as sort of the last thing that we're going to touch on. Our goal, identify and attend to the most important features in the input. How does this look like in an architecture, right? Our first step was to take this positional encoding, copy 3 times, right? We then pass that into 3 separate, different linear layers, computing the query, the key, and the value matrices, and then use these values, multiply them together, apply to scaling, and apply to softmax to get this attention weighting matrix. And our final step was to take that attention weighting matrix, apply it to our value matrix, and get this extraction of the features in our input that have high attention. And so it's these core operations that form this architecture shown on the right, which is called a self-attention head. And we can just plug this into a larger network, and it's a very, very, very powerful mechanism for being able to attend to important features in an input. Okay, so that's it. I know it's a lot to go through very quickly, but hopefully you appreciate the intuition of this attention mechanism and how it works. Final note that I'll make is that we can do this multiple times, right? We can have multiple individual attention heads. So in this example, we're attending to Iron Man himself, but we can have independent attention heads that now pay attention to different things in our input. For example, a background building, or this little region shown on the far right, which is actually an alien spaceship coming at Iron Man from the back. All right, this is the fundamentals of the attention mechanism. And its application, as I mentioned at the beginning of this section, has been most famous and most notable in these architectures called transformers. And they're very, very, very powerful architectures that have a variety of applications. Most famously, perhaps, is in language processing. So you may have seen these examples where there are these really large language transformers that can do things like create images based on sentences, for example, an armchair in the shape of an avocado, and many other tasks ranging from machine translation to dialogue completion and so on. Beyond language processing, we can also apply this mechanism of self-attention to other domains, for example, in biology, where one of the breakthroughs of last year was in protein structure prediction with a neural network architecture called AlphaFold 2. And a key component of AlphaFold 2 is this exact same self-attention mechanism. And what these authors showed was that this achieved really a breakthrough in the quality and accuracy of protein structure prediction. And a final example is that this mechanism does not just apply only to traditional sequence data. We can also extend it to computer vision with an architecture known as vision transformers. And the idea is very similar. We just need a way to encode positional information, and then we can apply the attention mechanism to extract features from these images in a very powerful and very high throughput manner. Okay, so hopefully you've gotten a sense over this course of this lecture about sequence modeling tasks and why RNNs as an introductory architecture are very powerful for processing sequential data. In that vein, we discussed how we can model sequences using a recurrence relation, how we can train RNNs using backpropagation through time, how we can apply RNNs to different types of tasks, and finally, in this new component of the sequence modeling lecture, we discussed how we can move beyond recurrence and recurrent neural networks to build self-attention mechanisms that can effectively model sequences without the need for recurrence. Okay, so that concludes the 2 lectures for today. And again, I know we're running a bit late on time, and I apologize. But I hope you enjoyed both of today's lectures. In the remaining hour that we have dedicated, it will focus on the software lab sessions. A couple important notes for the software labs. We're going to be running these labs in a hybrid format. You can find the information about downloading the labs on the course website, both the Intro to Deep Learning course website as well as the Canvas course website. All you will need to run the software labs is a computer, internet, and a Google account. And you're going to basically walk through the labs and start executing the code blocks and fill out these to-do action items that will allow you to complete the labs and execute the code. And we will be holding office hours both virtually on GatherTown. The link for that is on the course Canvas page, as well as in person in MIT room 10250 for those of you who are on campus and would like to drop by for in-person office hours. Alexander and myself will be there. So yeah, with that, I will conclude. And thank you again for your attention. Thank you for your patience. And hope you enjoyed it. Hope to see you in the software lab sessions. Thank you.